Okay, as I promised some of you, those who were absent, I'm gonna do this kind of like a review for you guys. It's chapter 7, similar triangle. Of course it's for geometry. And 7.1 is dilation, 7.2 is similarity transformation, 7.3, we can actually look over here, not that. We can actually look over here. So we did the dilations, similarity, transformations, and proving triangles similar. So these 3 chapters, we basically covered that for the last week or so, maybe the week before. And if you were absent, that's basically what you didn't learn. And the first one, dilation, there's a lot of drawing in there. It makes it a little bit difficult to draw, as in I don't have the setting for it. I couldn't draw it on a piece of paper. It's much easier to do it on a piece of paper than showing you how to do it. I can tell you the ins and outs of it, but learning how to do it, I would say really just look into your book. And I do want to point out something though, concept of dilations. So if you look into your book, there could be this. It's very early in one of the pages. So I think I told all the people in the class already, if you look into your book, they will actually give you 2 methods. Method 1 is called the ratio method. Method 2 is called the parallel method. I would say you should be focusing on the ratio method. Ratio method will work 100% of the time, and that works. So long as something works all the time, we are going to just use that. Okay, so this method basically said dilation, as the name implies, is going to enlarge or reduce the size of a shape. They will always have to give you something called the center of dilation and a scale factor. Hopefully you remember that in 6th grade you guys should have done something called scale factor. Scale factor basically is saying, like, if I have the measurement of this A prime and B prime and the measurement of this A and B, okay, I should be able to do a division. It doesn't matter which way. Well, it depends on the pre-image and image. So this is your pre-image. This is your image. So normally when you do the scale factor, let's just go over that just in case. It's about 7.1. Scale factor is that's how you do this. Scale factor, to find the scale factor of like one shape to the other one, I'm just gonna randomly draw something. Let's say I will draw this. Okay, and I'm going to do a dilation to this. Okay, enlarge this, make it a little bit bigger. So from this process, from the smaller one to the bigger one, we can say this is going to be the pre-image. This is the image. So the scale factor for this is, for example, I know the length of this square. Let's say this is going to be just 5. And for the other square, this is going to be 10. So the corresponding vertex. So let's just give you some name. Okay, we like to have names for things. So this is A, B, C, and D. So this is A prime, B prime, C prime, and D prime, because this is the image. So we follow the same naming convention and we just have the prime for it. Scale factor basically saying that you need to find the ratio between these 2 shapes. How you can do it, I will always have the image over the pre-image. Oops. Sorry. So in this scenario, I have 10 over 5. So I'll get a 2. Alright. So that means from the pre-image going to the image, I actually have to multiply everything by 2. So if you know this scale factor is going to work with one of this leg, you can check the other one. Okay, you can check the other one. So that is assuming you have all those length. Scale factor can also go the other way. For example, if you decide that, okay, I want to figure out like from the bigger one to the smaller one, what happened, you have 5 divided by 10 instead, because you're going from the image, the bigger image to the smaller one. So you have your result. Your result is 5 over 10, which is going to be a half. So the scale factor will have this property. From the smaller one going to the bigger one is 2. From the bigger one going back is going to be a half. Okay, so that's the idea of scale factor. That's why I was talking about it earlier, and which is the key for this topic. For this very first chapter, we spent a lot of time on drawing. Actually, that's basically what we did. I would say I'll give you like the point of dilation over here, and then we are going to extend this line, the point of a dilation, to one of the vertex. That's your pre-image. You're going to join this line, you're going to join all of that, you're going to join all of that. Then after that, you are going to measure, let's say, PB. Alright, you are going to measure PB. So PB may come out with like 10, and then your scale factor is going to be scale factor multiplied by the PB. So it will shorten your PB, and you ended up with this PB prime. And that's where you should put your image. Okay, so this whole concept of drawing, everything is going to be in proportion, which is the key for this. And if you have two similar shapes, all the sides are proportional. So you have the scale factor in place, and all of the angles are going to be the same. So that's what we call similar objects. A little bit different to congruence. Congruence objects, they have the same size and same shape. But for similar object, they will be of the different size, but then they will have the same angle. So 7.1, I actually had another video for it. I used GeoGebra to show you what it means by dilation and what's the effect of the how the points of dilation affects each of those translations. So you may want to check that out. 7.1 is really not too much things going on. It was just really about the scale factor, and see if we can find those scale factor most of the time. So if you look into the homework assignment, if there's any problem with 7.1, just remember that the key for this is always about the scale factor. So can you do this image divided by p-image, and whether we can get the scale factor or not. Alright, so 7.1 is really not too much of a fuss. But 7.2 is a little bit more difficult. 7.2 actually says if we have two shapes, we want to somehow get into what they call the similar or similarity transformation. Similarity transformation basically means, can we just exit out of this thing? Jeez. 1 second. 7.2, similar transformation. Similar transformation basically says from one shape to the other one, let's say from the smaller shape to the bigger one, there's always a composition of rigid motions. Okay, it's always the composition of rigid motions aiding a dilation. So the idea of that is 7.2 similarity transformation is composed of three things, or well, just two things: the rigid motion and a dilation. So rigid motions, they are the reflection, rotation, and translation, and then you add a dilation to it. So basically, if two shapes that look similar, let's say this triangle look very similar to the other triangle, they look very similar to the other triangle. So it should be a composition of rigid motions and a dilation to get the smaller one to the bigger one, as an example. So for this one, I can see that, oh, well, I can apply a translation. So I can do a T over here. So I can translate. So this smaller one ended up way over here. That would be my expectation. So it ended up over there, and then after that I'm gonna do a dilation with the point of dilation over here and extend it to size, and then I ended up with the red triangle overlap with your green triangle. So when that happens, I can somehow prove that two shapes are similar by rigid motions and dilation. So this is a way to actually show two shapes are similar. That is, going through some of the rigid motions, it could be like a composition of like a reflection, rotation, and translation, all three of them. But at the end, you're going to add a dilation to it. And then when the two shapes overlap, that's when you have the similar transformation. So similar transformation is actually one way to prove that two shapes are similar. So I actually have an example over here. I hope that will show you what it means. Actually, I have two. So for example, I have these two shapes over here. I have this bigger triangle ABC. I have a smaller triangle over there. Alright, so what I may want to do is, I normally would figure out the scale factor first. So let's just talk about that. I noticed that the AB is going to be correspond to my DE prime. I don't know why they have a prime over there. Maybe there are 2 points over there. Let's just destroy the E prime. Can we not show the E prime? Why do I have an E prime? By E prime. So I want to figure out the scale factor first. So you look at this bigger shape, you look at this smaller shape. The order doesn't really matter. If you like to go from this to that, it's okay. If you want to go from the bigger one to the smaller one, it's also okay. It doesn't really matter which way you go. For this scenario, I will go from the bigger one to the smaller one. So AB should be correspond to your DE. Corresponding sides, corresponding parts, they are very important. We started in parallel lines. So corresponding is a very important concept. So AB, we can see that it's like 1, 2, 3 is 3 dots. And DE is only 1, right? So the length is 1. This is 3. We can double check the other one. This is 1, 2, 3. This is 1 as well. So the scale factor is going to be divided by 3 or multiplied by 1/3. Okay? So I will always try to do the scale factor first. I want to make this shape a little bit smaller. So after that, I'm going to do a translation. So let's try to make this a little bit smaller. Scale factor is going to be dilation from a point. So I want to select this object. I want to select the point of dilation. Let's check it. Let's see if we can do this one, or B. So as I said, it's going to be divided by 3. Scale factor is going to be 1/3. So after that, that shape is going to be that one. Alright, it's going to be that one. I'll change the color so we are not going to get confused about this. So we'll have a green one over here. So this is a green one, and I'm going to move this to that direction. Agree? So we are going to move, let's say, this B prime all the way to E. It has to match. B prime is correspond to E. So I'm going to move 1, 2, 3, 4, 5 times. So the translation itself, if you don't know, is going to be, let me write that out. It's going to be translating 5 times on the x-axis or x value. Y is not going to change, so it's going to be a T50. If you're actually using GeoGebra, they're not too bright on this. The transformation, if you click on it, they say select the object to translate, then the vector. Vector, eventually you'll learn it. Vector basically is your translation. So I want to do, so I'm clicking on my vector. I'm going to do this. I'm going to move all the way to E. Alright, so I have to tell it what I have to do. That's my translation 50. Then we are going to click on, not dilation, transformation. So I click on the green one, click on my vector, then it overlaps. So just recap what I did. I started with the bigger shape. I realized there's going to be a dilation. So I shrink my bigger triangle and then I translate. Alright, so that idea, dilation and a translation, that is basically fall into the definition of similar transformation. I have the rigid motion somewhere, I have a dilation somewhere, then I'll end up with a similar shape. So long as they overlap, see, they overlap, I have the similar shape. I want to show you another one. This video may be a little bit long because I'm covering like 3 chapters. I want to look at it. I don't want to save. Can I just view? Oh, this is really annoying. But anyway. So let's say I have another one to play with. This time I don't have all those points anyway, so we may have to be a little bit careful about this. Okay. What happened? Okay. Now it's working. So I have this shape. I'm trying to map the bigger one to the smaller one. There could be many ways to do it. Alright, and that's why we are using this. I'm a lazy person. I like reflection, to be honest with you. But we can try rotation. Okay, I can rotate this shape down to that side and see if it works or not. But first of all, we want to do the dilation first because I think that's much easier to do. So hopefully you can see that this is the hypotenuse, so they're going to be corresponding. This one is going to be all the way down there. So 1, 2, 3, 4, 5, 6. 1, 2, 3. So in my mind, I'm thinking, okay, it's going to be divided by 2. And I have to check the other one. 1, 2, 3, 4, 1, 2. Okay, divided by 2. So I got that sorted out. So scale factor after 7.1, you should really know what you have to do with the scale factor. It's going to be divided by 2. Let's just do that first. So transform, can we do this? Reflect, translate, and can I have more? Scale factor. Okay, so we are gonna delay that half. So I want to click on it. I'm gonna delay it at this point, 0.5, right? So my shape will end up with that one. As I did that before, I'm just gonna do another color so it makes it easier to look at. Okay, so after this dilation, I am going to somehow get this shape to that side. So I can actually do a reflection over here by, let's say, the y-axis now ended up over here, but still that seems like it's a lot of work. Then I may try rotation. So rotation I can do possibly like 180 degrees. You can play with this. You can just draw it on GeoGebra and see if it works. I have a point at origin. We can just try that. We're gonna do this. We're gonna do this. We can try many. Let's say just try 45 and see if it's gonna work. That is not gonna work. I want it to go a little bit further, right? So I may want to try 90. The good thing about GeoGebra is you can really try many things. 90 is close. You can see that it's just one more swing to this direction. We'll get it. So 90 doesn't work. 45 didn't work. Let's try 180. See? So this, after rotation, I'll get it to this side. Is very close. So all we need to do is we have to translate this point all the way down there. So it's just going down by 2. So the vector is going to go down by 2. And on top of that, the vector itself is really not too bad on GeoGebra. You don't even have to figure it out. You just have to draw that. Why do I have so many things over here to click? So from here, going down there, then I can finally do the translation. Translation is this one. Alright, this is really annoying because their more has so much more things that I don't want them to do. Okay, didn't see that thing coming. So it overlaps. I'm sorry it takes forever because normally the menu is not that big and suddenly it's huge. So what I did over there was I did a rotation of 180 degrees at the origin, and then I translate it down by 2. So 0, -2. So that actually fall under a similar transformation. So for the second example, I started with a rotation of 180 degrees at the origin, okay, and then I did a translation of 0, -2, and of course I can't forget what we did right off the bat in the beginning. It was a dilation of 0.5. So 0.5 at the point of dilation, which is this -2, 1. So this is still under the understanding of similar transformation. You started with a dilation, then you have a rotation, and then you have a translation. Then it maps your original shape to the smaller one. Okay, it took a little bit longer than necessary, but the point being, similar transformation, at least, is a way to prove that two triangles are similar. So that's 7.2 for you. Alright, 7.3 actually is much easier to follow. 7.3, the world of math actually is much easier to understand because we actually did that before. 7.3, they said, is proving similar triangle. Oops. Proving similar triangle is actually quite simple. If you have two triangles, you suspect that they are similar. There are 3 ways to do it. First one, AA similar. Second one, SSS, similar. And last one, SAS similar. Very similar to the congruence triangle. These few things, the A and the S correspond to different meanings. A is the angle, S is the side. However, for a similar triangle, S means a little bit more, so A is just angle. So if the angles are the same, if they are the same, then you can use this theorem, AA similar. S, on the other hand, we are talking about scale factor. Okay, we are talking about scale factor. So for each corresponding side, I want to make sure that those scale factors are the same. Alright, so let's talk about AA as the first scenario first, and hopefully we'll get done soon. So if I have two triangles, it doesn't matter the orientation of it. So if I have two triangles, that looks like this. Alright, obviously they are different sides, and I know they look not wonderful. AA similar basically says, if you want to prove these two triangles are similar, let's call it ABC, JKH. If you want to say these two triangles are similar, all you need to know is 2 of those angles that are corresponding, by the way, let's say A and K, you know that they are the same. And you also need to know another one. So let's say B is going to be same as J, and they're also corresponding. So if you have this scenario, then they are similar. So as I said in class many times, giving you this theorem, you have to somehow prove it, and then you're going to write that, oh, triangle ABC is going to be similar, so be careful about that sign. It's going to be similar to triangle what? KJH. And the reason for that is AA similar. So you always ended up with like one statement. You're going to prove that two things are similar. Then you use the AA similar. And of course, you have to have those information in front of you. So without that, it's not going to work. Without that, it's not going to work. You gotta have those angles that are the same. And we are not going to use AAA because you can actually do that. If you know a pair of angles are the same, you can always get to the last pair. And the good thing is we don't need all of that. We just need 2 bits of information to prove this is going to be correct. Alright, so that's the AA setting. Just like congruence triangle before, you may be given a pair of triangles and you are going to figure out whether you have a pair of equal angles. Alright, next bit I think is side, side, side. So again, you have 2 triangles. I'm just going to do this. 2 triangles. One is, oops, oh my god. There are like many triangles. One is big, one is small. One is big, one is small. Okay. Assuming we know some of the numbers over here, let's say, let's just call this 2. This is going to be 6. 3, 9. I know you are thinking like they are equilateral triangle. Why are you doing that? I'm trying to prove a point. So 30. Okay. It's 2 triangle. It's not to scale. That's why. SSS basically said you want to compare each of those corresponding sides and their scale factor. A, B, C, X, Y, Z. Let's just do it like this. So you want to set up something like this. You want to compare their scale factor. What I mean by that is, let's say this is the image, that is the pre-image. I want to compare the XY divided by XY is going to be AB. It should be equal to your XZ over AC. We are checking out the scale factor YZ over BC. So this one, the very first one is going to give you a scale factor as the answer. The second one is going to give you a scale factor as the answer. The last one is going to give you a scale factor for the answer. That's what they mean by the S, S, and S. So this is the SSS similar. So it's not like congruence triangle. It was very simple. You just compare the length. They're the same. We call it good. This time we do have to do that little calculation over here. So we are going to check it. So you plug all the numbers in there, and XY is going to be 6. AB is going to be 2. The answer is going to be 3. Then I'm going to do the other one. XZ is going to be 9. AC is going to be 3, so it's going to be 3. YZ is going to be 30. Last one is 10. So we got ourselves the same scale factor. So in this scenario, I can use SSS similar to say that 2 triangles are similar, just because, you know, they have the same scale factor everywhere. Alright, so last one. I really want to be like shorter than 30 minutes. I'm talking too much on the snow day. I'll just draw it so people won't complain. That's a triangle. Okay, it is a triangle. I'm gonna draw another one that looks like this. So last one is called SAS, similar. So as the name imply, I possibly need to know the angle. One of them, they have to be the same. One of them have to be the same. Let's say this is the longest side. Let's just call it 5, 50, 3, and 30. Alright, so the checking this time is a little bit different. You are going to check this pattern. Make sure you have like, you know, the angle in between. Without that, you cannot use SAS, just like the congruent triangle. So I'm going to check the first S, which is 50 divided by 5, possibly. Check the very first scale factor. You get yourself a 10. This angle, let's call this A, let's call it X. Then you can say, well, angle A is congruent to angle X. And now I'm checking the last scale factor. Make sure that you follow the same pattern. If you start with the bigger one to the smaller one, keep that. So I have 30 divided by 3. So this last scale factor is going to be 10. And therefore, you get yourself SAS. So if you have two triangles with this scenario, then you get yourself the SAS. I know it's never gonna be as great as the lesson. We don't have the time. But I hope that helps you if you were absent. At least you have some idea what I did in class. All of this, all the things I talk about is actually the skills in each of those chapters. And what you need to do is you spend the time, go through the textbook, and use the skills. They are the core skills. If you were absent, obviously you didn't go through all those examples in class with me. However, I'm pretty sure you can, handle that, at least so long as you have the idea what we did in class. And if there's any problem with the homework assignment, just ask me. I'm more willing to help. But hopefully that will cover the 7.1 up to 7.3. Focus on 7.2 and 3. The understanding of the rigid motion with the dilation is important. Using the 3 theorems for proofs, also very important. And that's all for now.